Good morning, students.
Good morning, sir.
Okay, we'll continue with the lecture. Yesterday we had seen about the Bayes-Sauer's law. With the help of Bayes-Sauer's law, one can find magnetic field produced by a wire. Now we'll use that Bayes-Sauer's law to find magnetic field due to infinitely long straight wire. So now we consider a straight wire. So what we are going to use here is, see this is the yesterday what we have seen, a wire, not a straight, of any shape. Then element is there, dl, vector dl. It is tangential at that point. Then distance r is there. So this direction from the element to the point where you are finding the field. Then a position vector. To find position vector, we take the some origin, coordinate system we take, some origin. From origin to that element, position vector is r1, and from the origin to the point where we are finding the physical quantity, there is a position vector r2. So vector r1 and vector r2, I is the current flowing through this. So here, so this is the diagram we are considered, and this is the formula which we have written. So this is the formula for the magnetic field. Total magnetic field to the full wire field at a point P, it is given as mu naught I divided by 4 pi integral vector dl cross then vector r2 minus vector r1. See, this vector r1 and vector r2 are the position vector. Vector r1 is the position vector of the element, and vector r2 is the position vector of the point where you are calculating the magnetic field, divided by modulus. This is a modulus, means magnitude. Vector r2 minus vector r1 cube. So this formula we have stated yesterday. So this is a magnetic field due to the full wire. It is in the vector form. Now next what we consider is, say, we consider the wire kept on the x-axis. Say, now this is that wire. So this is the wire. It is a wire kept on the x-axis. It is infinite wire. So from the origin, it is extending to the plus infinity, and on the other side, it is extending to the minus infinity. So plus infinity to minus infinity. Then we find the magnetic field here at this point. So this is the point. At this point, we are finding the magnetic field. That is along the y-axis. Okay, so in this derivation, the wire is on the x-axis, and the point where we are finding the magnetic field is on the y-axis. Then, as I mentioned yesterday, that point where you are finding the magnetic field to the origin is vector r2. Now, beside this, we write this as a, distance a. So, point from the perpendicular distance from the wire is a. In terms of position vector, it is vector r2. Then, at some distance x, say x-axis, so at some distance x, we take the element. So, element length is dx here. So, it is the element, dx is the element. And direction of the element is this way. This is the direction of the element. This is the direction of that element. And the angle made by, see this element, see in this case, element to this distance from element to the point, that angle is theta. So here, this is element is here. Now element to the point where you are finding the magnetic field, that angle is theta. Okay, so we have translated this. See, we have translated this part. We have translated this part here. So in terms of this, we have written, we have marked there according to this main diagram. So this is angle theta. Then, so position vector of the element to the O is vector r1. Then this, the element ended point is vector r, the distance. It can be written as vector r2 minus vector r1. Then beside that, this is pi minus theta. Since this is theta, total is 180. So it is 180 minus theta. Okay, so this is how it is drawn here. Now, here what happens is, we are using this formula for the Biot-Savart's law. So this is the general formula for the Biot-Savart's law. So this is the general formula for the Biot-Savart's law. But here, see, the wire is infinite. So element extend from minus infinity to plus infinity. So that's why the limit here is minus infinity to plus infinity. Then, now this is a general formula. We have to write this in terms of this present situation of the infinitely long wire. Now, element vector dl, the magnitude of that here is dx. So dx is the element. Magnitude is dx. Now dx is the magnitude. So but dl is a vector dl. So this is the magnitude. So any vector can be written as its magnitude into the unit vector. Now since the direction of this element, direction of this element is along the positive x-axis. So you multiply by unit vector I cap. So vector dl is written as dx I cap. Then this we are not changing. Vector r2 minus vector r1 divided by modulus of vector r2 minus vector r1 cube. This we are keeping as it is. Now here, see dx modulus of vector r2 minus vector r1 cube, that is the magnitude. So what are the vectors here is I cap and vector r2 minus vector r1. So what is there? Integrand is the cross product. One vector is I cap, other vector is vector r2 minus vector r1. So now we'll evaluate this cross product. Evaluate this cross product. So when you take a cross product, that means the vector quantity. This is the vector quantity. So this is the vector quantity. And any vector quantity can be written in its magnitude into the unit vector. See, we have seen in the first term. Any vector can be written as its magnitude into the unit vector. Now magnitude of this vector I cap cross vector r2 minus vector r1 is a cross product. A cross B is AB sine theta. So A here is I cap. Magnitude of that I cap is 1. Unit vector. Then magnitude of vector r2 minus vector r1 is modulus of vector r2 minus vector r1. And this into sine of theta. Theta is an angle between I cap and vector r2 minus vector r1. See, the angle between this I cap, positive x-axis, and this vector r2 minus vector r1. So that is the angle theta. Then, so this is the magnitude 1 into modulus of vector r2 minus vector r1 sine theta. This is the magnitude. See, this is the magnitude. Now, how we get here k cap? That is unit vector. So now we have to find the direction of this cross product. Now to find the direction of the cross product, I cap cross vector r2 minus vector r1. So first vector is I cap is here. So angle is going from I cap to vector r2 minus vector r1. So take your right hand, keep the fingers curled from first vector to second vector. Say, take your right hand and keep the fingers curled from those 4 fingers curled from the vector I cap to vector r2 minus vector r1. Then the thumb will point in the direction of that cross product. Vector I cap cross vector r2 minus vector r1. So when you curl your right hand fingers here in this direction, the thumb will point out of the page. So it is pointing out of the page. So now this is x-axis is in the plane of the page, y-axis in the plane of the page, perpendicular to this out of the page. That is the z-axis. That means direction of that cross product is along the positive z-axis. That's why the unit vector along the positive z-axis is unit vector k. So that's why k cap is multiplied here. So this is nothing but magnitude into the k cap. It is a k cap is the direction of z axis, and the direction of this cross product I cap cross vector r2 minus vector r1 is along the positive z axis. That's why unit vector along that is k cap is multiplied. Okay, now we substitute here. Now when you substitute here, in this case, say dx is there, I cap cross vector r2 minus vector r1 is 1 into modulus r2 minus r1 sin theta k cap divided by vector r2 minus vector r1 cube. Then this k cap, it has nothing to do with the integral. You take it out. So mu naught I k cap divided by 4 pi integral of minus infinity to plus infinity, because you have to add the that element, magnetic field to element from minus infinity to plus infinity, because the shade wire is infinity long. So what remains is that dx sin theta modulus of vector r2 minus vector r1 whole square. Now in this case, say in this case dx is a variable, dx, so it is a variable. So one variable is x. Then theta. See, now here the element is in this position. If we take the, suppose the element is here, then what will happen is from here to here, angle will increase. If we take the element here, angle will decrease. Element can be here also. Element can be anywhere on the wire. So x is not a constant. X is a variable, because x can be anywhere on the wire. So element can be anywhere on the wire. So x is a variable. So this x is a variable. Then theta is also variable. Since x is variable, at different position on the wire, theta will be different. Theta is a variable. Then vector r2 minus vector r1. See, the vector r2 is a constant. See, vector r2 is constant. See, this vector ra is constant because that point P is fixed. But element can be anywhere. So R1 will be different. So R1 is different means vector R will be different. So vector R, that is R1, is also variable. So now in this case, there are three variables. The integrand contains three variables: x, theta, and vector R1. And it is not possible to integrate the quantity containing the three variables. So if your integrand should be containing only one variable. See, in this case, integrand means what is there inside the integral, contain three variables. So it's not possible for us to integrate it. So in that case, what we do is, we write the variables in terms of one variable. So now what we are going to do is, we write x in terms of theta, and this modulus of r2 minus r1 also in terms of theta. So the integrand will contain only theta. Then to find that, say now this is what we have done. See what is given here in the blue box. This is what we have done on the previous slide. And this is a diagram which is there on the previous slide. So now we want to find out x, dx, and modulus of vector r2 minus vector r1 in terms of theta. So to find that, see here in this triangle, see this triangle, PO dx, in this triangle, you take a tan of pi minus theta. This is pi minus theta, tan of pi minus theta. Tan of pi minus theta is opposite side divided by adjacent side. Opposite side is A, is vector R2, or we have written it as A. Opposite side is vector A. Then the adjacent side is X. See, tan of pi minus theta is opposite side is A, adjacent side is X. So A by X. Then tan of pi minus theta is minus tan theta. You can use that and see. Tan of pi minus theta is equal to minus tan of theta. So then we simplify and write here this x equal to a by minus tan theta. And minus a is there. 1 upon tan theta is cos theta. So x equal to this. See, this is the x. X equal to this minus a cot theta. Okay. Then differentiate this with respect to dx by d theta. That means dx. A is constant. The derivative of cot theta with respect to theta is, see, derivative of cot theta with respect to theta is cos x square theta minus cos x square theta. because derivative of tan theta is sec square theta, and derivative of cot theta will be minus sine cosec square theta. So minus minus become plus, so this plus will be there, and a is there, cosec square theta and d theta. So when you say dx by d theta is a minus cosec square theta, so minus minus plus plus a cosec square theta, so dx equal to plus a cosec square theta d theta. So afterwards we can substitute this. So we have written this dx in terms of theta. Then next we want to write modulus of R2 minus R1. So you have to write the modulus of uh, R2 minus R1. This you have to write in terms of theta. See in this equation 1. See this. So in order to do that, again in the same triangle, take sine of that pi minus theta. Sine of pi minus theta. Sine of pi minus theta is opposite side divided by hypotenuse. Opposite side is a, so it is magnitude you have to take a, and hypotenuse, length of this hypotenuse is modulus of vector r2 minus vector r1. Magnitude. See finally sine of any angle is opposite side by hypotenuse. So it is the magnitudes which are given. So a, opposite side is a, and the hypotenuse is modulus of this vector r2 minus vector r1. So modulus here. Then sine of pi minus theta, you can expand that. Sine of a minus b, and you will get sine of theta. And a modulus of r2 minus r1. So when you simplify this, you get modulus of vector r2 minus vector r1 equal a divided by sine theta. 1 by sine theta is cosec theta. So this is a cosec theta. So we have written this modulus of r2 minus r1 in terms of theta. We have also written, see we have written this dx in terms of theta, then this quantity in terms of theta. Okay. Now we have to get the limits. See here this minus infinity to plus infinity, it is the limit for x. See x is going from one end. See x is going from minus infinity, it is going to the plus infinity, minus infinity to plus infinity. So that is the value of x. Now we want to find out corresponding to that x what is theta. Now when x is infinity, that means if you take this, if you shift this element here, x increases. Then if you draw here like this, then what you will find that angle increases. Angle will increase. So now as you go on taking this dx away and away from the origin, the angle of theta will become more and more. Angle will become more and more. Now limiting place. So when it is at infinity, then maximum it will take is 180 degrees. One is almost it will become parallel here. When you take this dx to infinity, it will become, this line will become almost parallel. So that's why as x tending to plus infinity, theta will tend to pi. Pi means 180 degrees. Now if you take this element on this side, say this is the angle. See this is that angle theta. This is that angle theta. Okay. So now what happens is, so if you take the element at the origin, then theta will be equal to 90 degrees. If you take it away on the negative side, theta will become less than 90 degrees. It will become less and less. And if you take it to infinity, see if you take it to infinity, minus infinity, then what will happen is, it will become less and less. So this line will be almost parallel to the x-axis. So theta will be almost tending to 0. So x tending to minus infinity, theta tending to 0. X tending to plus infinity, theta tending to pi. So this is the limit. So now we have in this equation 1 dx, we have modulus of r2 minus r1 square, and then we have also limits. That limit for theta, you will go from the this 0 to pi. Okay, so this we are going to substitute all these things, these dx, then modulus of r2 minus r1, and these limits we will substitute in the equation 1. So we are doing it here, we will substitute them here. See, equation 1, then dx we have, then modulus r2 minus r1, and that limit we know 0 to pi, we substitute here. Now in this case, see, this cos square theta cancels, 1a cancels, then 0 to pi, So what remains there is sine of theta divided by a d theta. A is constant, you take it out. So what you'll get is here mu naught I k cap divided by 4 pi a inside the integral sine of theta. And integral of sine theta is minus cos theta. See, integral of sine theta is minus cos theta. So limit is from 0 to pi. So this is minus. Then you take that minus outside. We have taken the minus here. We have taken the minus here. And you substitute the limit cos of pi, upper limit, substitute the theta equal to pi and theta equal to 0. So substitute the upper limit minus lower limit. Then cos of pi is minus 1 minus cos of 0 is 1. Then minus 1 is minus 2. So minus minus cancel become plus. And what remains here 2. Then this 2 will cancel with this 4 become 2 here. And what you get is vector b equal to mu naught I k cap 2 pi a. So direction of vector b is along the positive z axis. And the magnitude of this, if you take a modulus of this, then what you will get is b equal to mu naught I by 2 pi a. B equal to mu naught I divided by 2 pi a. Now, this is the formula for the magnetic field at any point on the at a certain distance a from the wire. Now, this formula is not new for you. In the 12th standard, you have studied about Biot-Savart's law. Then you have derived this formula that time in 12th standard by using what is called the Ampere-Circuital law. We will also do that. In this chapter also we will do it, but later. Okay? With Ampere-Circuital law, you can get this formula in some few steps, 2-3 steps. So here it is a lengthy, okay, but it is there in your syllabus. Derivation of magnetic field using Biot-Savart's law. So there symbol you are using, instead of A you are using R. So in the 12th standard you have to use the symbol R. You said mu naught I divided by 2 pi small r. Here I am taking the textbook from your the symbol from your textbook, Rich and Milford, where they use A. Okay, I am using a standard symbol as given by the prescribed textbook. So it is mu naught I divided by 2 pi A. Okay, so that means larger current, more current will flow. Larger distance, less magnetic field. Now for at the same distance, say at the same distance, the magnetic field will be same. That means when you have a straight wire like this, then at the same distance around this, at the same distance around this, at the same distance around this, at a distance A, the field will be A. That means, say, now this magnetic field, this line is perpendicular to the wire. Okay, to the wire it is perpendicular. That means around the wire, at each and every point, magnetic field is there. And at in the concentric circle, a given concentric circle about the wire, the field is same. So if you take a concentric circle of the larger radius, then field will be less because the distance is more. But at each and every point on this circle, see around this, now these circles what I have drawn are the horizontal circle. Around that, the field will be same at the same distance. Okay. So in fact, these represent, see what I have drawn here dotted line, these represent the magnetic field lines. These are magnetic field lines. And to the field lines, if you draw the tangent, then that gives the direction of magnetic field. Okay. Direction of the magnetic field will be tangential to this. So given wire like this, okay, is in the vertical wire. Let us say wire is vertical. Then the concentric circle. See this concentric circle will be in the horizontal plane. Concentric circle is horizontal plane. And here what happened is at each and every point the field is same because it is at a same distance from the wire. And so this represents the field line. And if you draw the tangent, that gives the direction of magnetic field. So that is just like a regular electric field and the direction of electric field. Same way here magnetic field also. Okay, tangent. So tangent means, so wire is vertical, the field will be horizontal. Okay, perpendicular to the wire. Okay. Now this way you can find out, you can find a direction. You can find the direction of the wire, but also there is a mechanical rule to find out the direction of the field produced by the wire. So that is given as right hand rule for the straight wire. Therefore, In fact, in this magnetism, there are many rules. In the right hand thumb is used to find out the direction of the cross product. Then the right hand thumb rule is used to find the direction of the magnetic field of straight wire, and of course, we also use for a circle. But here, right now, we are using for the straight wire. Now you can get it even using the Biot-Savart's law. See, if you are using the Biot-Savart's law, then what you would find is direction of dl cross r. That will give the direction of magnetic field. But there is a mechanical rule for a straight, especially for the straight wire. There is a mechanical rule. So what is to be done is, see, you have to read this and just imagine. Hold a wire in the right hand. You have to catch the wire in the right hand. Example, you can consider a pencil or a pen. Okay, pencil and a pen. Hold it in your right hand. You should not hold it in your left hand, but you should hold it in the right hand. Then you have to hold it in such a way that thumb points in the direction of current. Alright? Suppose you have taken a pencil. The pointed part, sharpened point, the part of the pencil is the direction of current. Then you hold that in your right hand with the thumb pointing in that direction of the pointed part. So direction of the current. Then the four fingers will curl around that pencil. That means it will curl around the wire. Now that four fingers points in the direction of magnetic flux. And if you draw the tangent to that, that gives the direction of magnetic field. Example here. So example here. Consider this case. This is a wire, straight wire. This is a straight wire. And this is the direction of current. So it is the direction of current. Hold this wire with your right hand. Thumb pointing the direction of current. The fingers are curling like this. Fingers are curling like this. Okay. So now this the fingers will curl like this. So this is the direction of the flux. Flux will circulate like this. It is a closed path. See, magnetic flux is a closed path. Magnetic field lines are a closed path. Electric field lines are not closed. They originate from positive charge and terminate on the negative charge. But magnetic field lines form a closed path. They are not open. This is the direction of the flux. If you draw a tangent to that fingers, then it gives the direction of magnetic field. Okay. Suppose the direction of current is downward here as well. So hold your right hand with the thumb in the direction of current. Okay. Then the fingers will curl like this. So fingers will curl like this. So that is the direction of the flux. If you draw a tangent to that at any point you can draw the tangent. That gives the direction of magnetic field. Example here. Consider this diagram. I have drawn a straight wire. This is the current, and using the right hand thumb rule, I have drawn here this circulating flux. See, this circle which you see is a flux. See, the thumb is in this direction. So the fingers will circulate, curl in this direction. So the direction of the curled fingers is the direction of the flux. It is the direction of the flux. This is the direction of flux. Then you draw the tangent. If you draw the tangent here, it will be horizontal towards your right. There is a direction of magnetic field at this point. So there is a direction of magnetic field at this point. Now here, if you draw a tangent, the tangent will point perpendicular inside the page. It is perpendicular inside the page. So that's why I marked here cross. So this I marked here cross because these fingers will curl inside this. Now if you consider on the other side of this circle, that fingers will curl this way. Fingers will curl this way. If you draw the tangent here, exactly diametrically the opposite end to this, then the tangent point this way. So this is the direction of magnetic field at this point. Then if you come to this point, then the fingers are curling this way. So from this point, the fingers are coming out. So if you draw the tangent, it will point outside the page. So that's why I shown here a dot here. So that is the direction of magnetic field. Okay. So that means, see, for a magnetic field due to straight wire, we don't use the to find the direction. We don't use that direction of vector dl cross vector r. We use this right hand thumb rule. So see, suppose wire is like this. Then on this side, the magnetic field will be inside. On this side, it will be outside. That is done by keeping the thumb in this direction of current. The fingers are curling this way. It is horizontal direction. Okay. So these fingers are pointing inside here. So direction of magnetic field is perpendicular inside at this point, and direction here, the fingers are coming out. So it is perpendicular pointing out. This is how to find out the direction. Then one more thing is, this is how to find the direction. Note is given here. At a point along the wire, field is 0. Suppose you take the point, this point is on the wire. Let us say the point is here. Suppose the point is here. Then what will be this theta? See, what will be this theta? What will be this theta? Theta will be, see, if the point P is here, if the point P is here, then this is that vector R2, then element is here, vector R1, and this angle is 180 degrees. And if you use the Biot-Savart's law, sine of 180 degrees is 0. So magnetic field will be 0. Magnetic field due to each element is 0. So magnetic field due to the full wire will be 0. So suppose you take a finite length of the wire. At any point along the wire, say at any point along the wire, the magnetic field is 0. So at any point in line with the wire, the magnetic field is 0. Okay, then you consider this problem. In the problem 2 given in your notes, find the magnitude and direction of magnetic field at distance 1 meter below the wire kept horizontally, carrying a current 10 amperes in the west-east direction. See, now to find the magnitude, very simple. You don't have to think. Formula is mu naught I divided by 2 pi a. Mu naught is 4 pi into 10 raised to minus 7. I is a current 10 amperes. 2 pi 2 into 3.14. A here given is 1 meter. Is 1 meter. A is 1 meter. You will get this answer so many Tesla. So it is direct substitution. Now to find the direction of the field, So now it is given here. Say the wire is, say first you have to draw horizontal plane. Say I have drawn here horizontal plane. This is the horizontal plane. To get a direction, horizontal plane. This is the horizontal plane which is drawn there. Then draw the line like this. Two perpendicular lines in the horizontal plane. Mark this as east. Mark this as east. If you mark this as east, other side will be west. Then if you face east, to your left it is north. To your right it is south. This direction you should know. If you face east, to your right is south. To your left is north. So this direction, east, west, see, in fact there are 8 directions, 10 directions, east, west, north, south, then northeast, northwest, southeast, southwest. Beside that 2 more directions are there, up and down. These are 10 directions. So to specify the exact direction, you have to give the 10 directions. So this you should know how to draw. These directions, east, west, north, south, that is in the horizontal plane. East, west, north and south. Then it is given there, the wire is the wire carrying a current in west-east direction. See, it is shown here. This wire, see, it is drawn here. This wire is carrying the current in west to east direction. And you have to find the magnitude and direction of magnetic field at distance 1 meter below. So here, at this point P, below you have to find out. Okay? So now to find the direction, you can use the right hand thumb rule. So what you do is, imagine, you keep the thumb in this direction, and catch this wire, hold this wire, see, hold this wire. You keep that, hold the wire with the right hand. Just imagine, you are holding the wire in the right hand, with the thumb in the direction of current. So this is the direction of current, thumb is there. Then, see, the fingers will curl like this. It will be in the vertical plane. So like this, it will curl like this. So in the page, it will go inside. So what happens is, from other side of the wire, it will come out of the page and it will go inside the page. It is going inside the page. That means the field is, see, the field here is inside. Field is inside. So at this point P, see the fingers will curl like this in horizontal plane like this. Fingers are curling in horizontal vertical plane. So it is coming out from the page and going inside the page. That means the field is inside. Inside here means from south to north direction. Say south to north direction. So the field is from south to north direction. That is how it is given. Directed south to north. Similarly, you go to the next problem. Find the magnitude and direction of magnetic field at a distance 1 meter east of the horizontal wire carrying a current 10 amperes in north-south direction. To find the magnitude is very easy. Mu naught I by 2 pi a. Mu naught is 4 pi into 10 raised to minus 7. This you know. Current is given 10 amperes. The distance is given 1 meter. Pi is 3.04 and you can find that 2 into 10 raised to minus 6 Tesla. Then to find the direction, see, it is given north south direction, it is given east given. So first you have to draw the direction. So draw the horizontal plane, then draw mark that east, opposite to that is west, to the left is north, and to the right is south. Now what is given here is the wire carries a current north south direction. See this wire carries a current in the north south direction like this. And where you have to find the value? At distance 1 meter east of the wire. So from the wire east side. So in this direction, see to the east. So the point P is to the east of the wire. Now we want to find this. What is the direction here? It is in the horizontal plane here. So now what you do is you hold this. Imagine that you are holding the wire with thumb pointing in the direction of current. So fingers will curl like this. So the curl finger will come out from this plane and going inside the plane. Say now this curl fingers, this direction is vertical. So from here it is coming above that plane and going inside the plane. That means see the fingers will curl this way. That means it is coming uh, out of that plane, out of this plane. See, I'm saying this plane. This plane is horizontal. So it is coming perpendicular out of this plane. That means it is in the upward direction. See, perpendicular to this plane. Coming, this is a plane, this is a horizontal plane. See, this is a horizontal plane I have drawn here. And these fingers are horizontal plane, this coming out of that plane vertically up. So that's why the magnetic field is directed vertically upward. Okay. So with this, I'll stop and continue tomorrow. Thank you very much.
Thank you, sir.
Okay.